folks. Welcome to the first video for Unit 3. Today we're going to start the unit on intersections of lines and planes. This is a shorter unit. We'll likely be having a unit test the second Monday after March break, which means that we'll be done this unit by Thursday or Friday of the week after March break. Today we're going to specifically look at the intersections of lines with planes, so how a line and a plane can interact. We need to define a few things first, and those would be what a consistent system is and what an inconsistent system is. A consistent system has at least one solution. Okay, it could have more than one solution, but it has at least one. And an inconsistent system is a system that has no solutions. We want to remember something from grade 10 when you were working on intersections of lines. If you end up getting, at any time, 0 equals 0, this is math's way of telling you that the system you're looking at has infinite solutions. Okay, so if we're working on some problems today and you see something like 0 equals 0, then you know that system has infinite solutions. On the other hand, if you get a solution like any number equals 0, so 5 equals 0, negative 7 equals 0, this is math's way of telling you that what you're looking at is false, and there are no points of intersection. Okay, so two things to keep in mind as we start working on this. So let's start with an example. We want to solve the following systems of equations. So I'm going to start with the equation of a line that starts at the point 1, negative 6, and negative 5, and is pointing in the direction of 2, 3, and 2. And I want to see how this line interacts with the plane 4x minus 2y plus z minus 19 equals 0. So we have a line, and we want to see how it interacts with the plane. So we need a plan as we approach this. What we're going to do is rewrite equation 1 using our parametric equations. Next, we'll sub the parametric equations into equation 2. We're going to isolate and solve for the parameter t. And then we'll sub the parameter t back into the parametric equations in order to get the potential point of intersection at some coordinate x, y, and z. So those are the 4 steps we want to follow. So to follow step one, I'm going to take my equation of a line, and I'm going to break it up into x, y, and z components, or parameters. So my x parametric equation is 1 plus 2t. My y equation is negative 6 plus 3t. And my z equation is negative 5 plus 2t. And I'm going to take these three equations and I'm going to sub them into my Cartesian equation of the plane. So subbing them in, I'm going to have to do some algebra to solve for t. Distributing, we get 4 plus 8t plus 12 minus 6t minus 5 plus 2t minus 19 equals 0. I want to isolate and solve for t, so I'll gather up all my like terms. I get 4t minus 8 equals 0. Or 4t equals 8, which means that t equals positive 2. So if there is an intersection between our line and our plane, the intersection happens when t equals 2. My very last step now is to sub in t equals 2 to my parametric equations. And this is going to tell me my point of intersection, if one exists. So when t equals 2, I get an x-coordinate of 5. I get a y-coordinate of 0. I get a z-coordinate of negative 1. So since all of these substitutions have given me one specific value, I can say that the point of intersection of the line with the plane is happening at the point 5, 0, and negative 1. If I wanted to double check and verify that this works, I could take this point of intersection, substitute it back into the Cartesian equation to make sure that I end up with 0 on both sides of the Cartesian equation. Okay, another example. We have a parametric equation of a line and a Cartesian equation of a plane, and we want to solve, see how they interact. So we're going to do the same thing as in example 1. I'm going to take these three parametric equations and I'm going to sub them into the Cartesian equation. So I'm going to get 2t plus 4 times 1 minus t plus 2 times negative 4 plus t minus 4 equals 0. So distributing, I get 2t plus 4 minus 4t minus 8 minus 8 plus 2t minus 4 equals 0. So grouping, I get 4t minus 4t minus 8 equals 0, and our variable is going to cancel out and end up with the statement minus 8 or negative 8 equals 0. And this is math's way of telling us something. This means that there is no point of intersection between this line and this plane. So there's no point of intersection. If we think about that, there's only one possible way that a line will never interact or intersect with a plane, and that is when the line is parallel to the plane. Okay, last example that I'm going to do, one more, solving systems. I'm going to take this parametric equation of a line, sub it into the Cartesian equation, and when we do, I'm going to get negative 4 plus 3t minus 2 times 0 minus 3 times t plus 4 equals 0. So negative 4 plus 3t minus 0 minus 3t plus 4 equals 0, and look at that, everything on the left-hand side is going to cancel each other out. And I get 0 equals 0. This is one of those special cases where math is telling us that there are an infinite number of solutions. And there's only one way this can happen. This is always true, and that means the line is on the plane. So when we're dealing with lines and planes, there's three cases for how a line can intersect with a plane. You could have a line passing through the plane and intersecting the plane at one point. So we get one point of intersection. Okay, that was the first example. We could have a line that's parallel to the plane. So this will never cross the plane, so we could have no points of intersection. Or we could have a line that's sitting on the plane. And if it's sitting on the plane, we have an infinite number of intersections. Okay, so that's where we'll pick up on the first Monday back after March break. Appreciate you watching this, and I hope you enjoy your March break, and I'll see you soon.